Hello, this is video 34, and this is a continuation of the RBT, Red Black Tree Q&A. Everything's abbreviated. I think you're required to do that in computer science. Don't ever use the full name of anything. RBT Q&A, and we were up to question number 4. Moving right along. How do we split a red box? And when? When do we do that? How? With a capital H. Looked like an A, didn't it? How do we split a red box? When? When are we going to do that? Two-part question. Q over here for question. A over here for answer. Let me squeeze a better Q in there than that. Q. There. It's miniature, but it's good. When? I'll do the when part first. When? Funny you should ask. On the way down the tree, comma, whenever, WHENEVER, we reach a full red box from above. Now, that could be kind of a cryptic answer. What does that mean? On the way down the tree, asterisk, footnote. On the way down the tree, things that we're doing on the way down the tree happen before we make the recursive call. We do it, and then we go to the left or right child. And then we do it again, then we go to the left or right child. And the doing it is splitting if we need to. That's stuff we do on the way down the tree. Before there's more than one recursive call. Before the recursive calls. I like that better. Why is it plural? Oh no, that's scary. Well, we might make a recursive call to the left, or we might make a recursive call to the right. Duh. Billie Eilish reference. Whenever we reach a full red box. Well, double asterisk. How do we know we've reached a full red box? I'll define it. Seat of the pantsley. Full red box. We know we're there. We know we've hit a full red box when we get a black node that has 2 red children. Full red box. Black node with 2 red children. A red child on the left, a red child on the right, and it's a black node. Now, what about a black node with a red child and then a red grandchild, either on the left or the right? If we've implemented everything else correctly, that's not possible. It's almost like this function is going to need its very own class invariants. Maybe we should call them function invariants. If we've constructed the tree correctly up to this point, we could possibly run into a black node with 2 red children. We should not run into a black node that's got a red child that has another red child. Why? Because that should have been fixed before the last return from put. If we have 2 red nodes in a row, that means the put function didn't do its job correctly the last time we called put. So all kinds of footnotes and stuff. Let me read this and see if I can put it all back together. This was supposed to be the easy part of that question. The when. When do we split a red box? We split it on the way down the tree, which is before the recursive calls to the put function. Whenever we reach a full red box, how do we detect a full red box? A full red box is a black node with 2 red children. Now, why did I tack that on there? Just to make it even more unnecessarily complicated? No. From above means we're going down the tree. As we're going back up the tree, we might very well, when we do our balancing around of the dog leg, 2 red nodes in a row, or a straight case of 2 red nodes in a row, we might very well balance that before we come back up. But it's okay to leave a full red box on the way back up the tree. Cool how that works. And you can go back and review the example. That's part of what I did the example first. Imagine if I were telling you all these things, if I were preaching this sermon, and you hadn't seen any examples of red, black trees yet. You're welcome. That's why I did this one backwards and did the example first. So you can go back and see cases of this where we reach a black node with 2 red children from above, and the other cases are not possible. Now I'm repeating myself in an infinite loop. How do we do it? Well, we draw a picture. So how do we split a red box? I'll even draw a line between the answer. Draw a picture. I think I'll have to put in my will to leave that on my gravestone. Draw a picture. 1957 to 2020. Okay, here's the before. Oh dear. I'm going to start with the red box to try to avoid as much smearage as possible. You might think, you know, this is just one little piece of the tree. How complicated can it be? Well, think a little harder. Here's what I'm going to call, D1 up here. Abstract for data value number 1. Down here is D0, data value number 0. And here's D2, data value 2. And of course we know, since this is a valid red-black tree up to this point, because everybody's been playing nicely by the rules the way they're supposed to, D0 is less than D1 and that's less than D2. D1, in the general case, will have some parent in the sky up here and another red box up above it. And I'll draw the red arrows, try not to smear. D0 and D1 are inside the red box with their parent. They might very well have non-trivial, maybe even huge subtrees of their own down beneath them. I'm going to call those, I guess I'll draw the triangles first. This is subtree T sub 0. That means the child of D0 to the left and all of the subtree beneath it. That little triangle represents all of that. There could be hundreds of nodes or even thousands of nodes. Don't know, don't care. Okay, on the right-hand side, we've got subtree capital T sub 1. D2 could very well have 2 non-trivial subtrees of its own. And we know, just a little point of trivia here, we know all those trees are about the same size because this tree is almost completely balanced. By design, otherwise we're wasting our time here. T2, T3, T2, T3. All of that is just the before picture. What does it look like when we reach a red box from above that's full? That's what it looks like. After. Gotta leave even more space for after. Well, D1, when we split this, let me review this here. On the way down, whenever we reach a red box from above. So we're moving down the tree, we're doing the put operation. Here's the weird thing. We gotta do this even if that data value is already in the tree. We don't know that. And we need to brace ourselves and be ready for it when we get to the bottom of the tree. And if we find it, we'll still return false, but we might have restructured the tree on the way down. Sidetracked myself. This is a full red box, a black node with 2 red children, this. The after picture, D1 has to move up and live with its parent. I'm gonna put it way up here in the sky. And it will, in the general case, now have a red incoming arc from its parent, because it moved back home. It's in the same red box as its parent. D0 and D1 get their own red boxes. I'll go ahead and draw those. Observing the anti-smear marker convention. D0, D2. Now with red arcs. Look at that. That's not a red arc. That's a black arc. That's a black arc. That looks like an exclamation point. That was supposed to be D1. Okay, let me say it again. Misspoke. D0. What am I doing? It's not pointing to the box. It's pointing to the node. I'm all coffeed up and everything. I don't have any excuse. There. That's part of it. D1 has a red incoming arrow from its parent that is not really a direct player in this operation here. D0 still has its 2 kids. Thank goodness we didn't have to shuffle the kids around. D0 still has subtree T0 and subtree T1. And D2 still has a left subtree T2 and a right subtree T3. Like so. And I hope I drew that picture correctly. I'm stumbling over it so much. Okay. What have we got here? The before picture, we hit a full red box. The after picture, D1 becomes a red node. Now, even though I'm drawing all these circular nodes in black, their color is determined by the incoming arrow. So these two are red nodes. They have red incoming arrows. That was on the previous board. This is a black node because it has a black incoming arrow. And D1 has a black arrow now pointing to D0 rather than a red one. And D1 has a black arrow pointing to D2 rather than a red one. Okay. Now, I'm going to leave that picture on the board, and I'm going to keep going because I want to say something about this. It's still RBT Q&A. That was question what? I don't even remember. Question 4. I'm going to call this question 4A. It is so closely, I'm sorry to mess up your numbering system, but it's so closely related to this that I think we need to address this before we go one step further. Question, how is a red box implemented? You knew it was coming. Oh dear. Well, we're going to have to summon all of our expertise and prowess in data structure development and C++ syntax and all that stuff. How are we actually going to implement one of these things? It looks like what? It's going to be a structure with 3 nodes in it, but we're not going to put these 3 nodes in an array. I mean, that's the whole point of graduating up from a 2-3-4 tree to a red-black tree. So I guess it's going to be a structure that has a BST object inside it to hold D1, D0, D2. And when we split it, I don't know, maybe we free up the BST that holds the nodes. I'm messing with you. I really am. And you're going to think I'm messing with you now when I write the answer. How's a red box implemented? It isn't. Red boxes are a figment of our collective imagination. We don't represent the red box in our RBT class. How can we get away with such madness? First of all, the reason it isn't, it's what we in the biz might refer to as a phantom data structure. It's there to aid intuition for the software designer. We can draw pictures of red boxes and figure out what algorithms we need to follow to be able to make this picture do what we want it to do. It turns out, when it comes down to the implementation, there's no reason to explicitly represent a red box. We've got all the information we need and everything else that's already there with one tiny tweak. It isn't, but the node structure from the BST. I hope I'm using the, how's a why can't I say that? How is a red box implemented in a red-black tree? The answer is, it isn't. Dun, dun, dun. But the node structure from the binary search tree will, oh, there is still a big change. We'll need a color field. And to refresh your memory, field just means it's one of the variables inside the structure. So in addition to having a left pointer and a right pointer and a variable to hold the data value, we also need some representation of color. Now make that a colon instead of a period. How do we represent color then? Well, we're smart enough to figure that out. There are only 2 possible colors, red and black. So it could be, I'll do some examples. It could be a Boolean variable called isRed. That's kind of a conventional way to name Boolean variables that are saying yes or no about something. If is red is true, then guess what color it is? You are right, red. The only other possibility, if is red is false, and it's black. Now, I don't have room to write a bunch of stuff here, but this could also be an integer. You could make it 1 and 0. I don't recommend making it strings. That's moving away from simplicity toward more complexity. With strings, you might have to be careful. In some places, you might accidentally put a capital R on red, where it's other places supposed to be lowercase r, R-E-D. Yeah, that's adding complication where you don't need it. There'll be plenty of fish to fry here. You don't have to add new problems. So again, since there are only two possibilities, Boolean is a natural choice. If you want it to be 1 and 0, that's fine, or some other representation. That could also be fine. What's not fine? What's not fine is, I still didn't really answer question number 4, did I? How do we accomplish a split? And maybe I've made that even more confusing. How do I split something that doesn't even exist? Yeah, that would be tough, wouldn't it? Let's look, if we ignore the red boxes in these pictures, which we might as well, they don't exist. They're for our benefit, so we can draw the pictures and know what we're doing. Look at the difference between these two. D1 used to be a black node. Over here, it's a red node. Things that make you go, Look at D0. D0 used to be red, now it's black. D2 used to be red in the before picture, now it's black. And ladies and gentlemen, there you have it. I'm not even going to elevate this to writing a function on the board, but let's say we do have a split function. Imagine with me. In C++, let's have a split function. We're going to pass in a root. We don't even have to remember to pass it in as a reference to a node pointer. We could just pass in a node pointer because we're not interested in changing the value of the pointer. We're interested in changing the colors. All we got to do from get to here is change it from a black node with 2 red kids. Change all 3 of the colors. You don't even have to look and see what they are. You know what they are when you do the test. Did I just now run into a black node that has a red left child and a red right child? If the answer is yes, then change the colors of all 3. Go from black with 2 reds to red with 2 blacks. And you may be thinking to yourself, that is just way too simple. I just don't trust that at all. That's just too good to be true. Sometimes things that seem too good to be true can actually be true. And this one is true. It's about time to have something like that in 2020. Something that's too good to be true, but it actually is true. I'll review that again. I went through that so quickly. There's just not much to it. You pass in root, a local variable. We're taking a local view here in our recursive function. We pass in a root, which is the address of node where we currently are in the tree with our put function. Pass in root. We do a quick test. Is root black and its left child is red and its right child is red? If the answer to that question is yes, then change the colors of all 3. If the answer is question of no, no harm done. You don't even return a Boolean value. You can make it a void function. Either it will realize that it needs to do a split and it does it, or it's going to leave it alone. It doesn't matter. It's got to be done on the way down the tree, and there's no reason to test to see if it was done. If it was done, it's done, and the tree has been updated, and that's all there is to it. And I'm absolutely repeating myself again. I don't know what else to say about this, except that I filled up the board again, even though I'm not done with questions. So this is going to be a multi-part video on one discussion. I'll see you online.